Well, it's the value of x that makes either of them not defined. And we know when you have fractions, which is what a rational expression is, that you cannot divide by 0, which means that x cannot equal to 2 in either of those two cases. Would you agree? Nothing complicated about that. Sketch the graphs of these using a graphing calculator. So our goal here is not to learn how to sketch these functions on paper. It's simply to learn from looking at the graphs what's going on. So my first function is, I just need to go back and take a quick peek at it, x squared minus 8x plus 15. Again, you need the numerator in brackets, everybody. So we have in brackets x squared minus 8x plus 15, close brackets, divided by in brackets x minus 2. We'll just double check that. And I'm going to choose to go zoom 6. And what we get is that graph. By the way, for those of you that have taken calculus, there is a slant asymptote there. You can see it. If you're in calculus, you know what I'm talking about. If you're not, don't worry about it. So that's what we are looking at here. And, you know, I don't think we need to worry too much about a perfect sketch, but we want to do a fairly decent job. There are two kind of pieces to this function. Let's put in the fact that we have a non-permissible value, first of all, at 2. And you can even see when you look at the graph, everybody, that there is a vertical asymptote at 2. The graph has a curve to it that is going up here against the asymptote and down here against the asymptote. Okay? And to be honest, I really don't care about much else in this graph, but we're going to sketch it. We can see that what it looks like is it goes up a little bit and almost maxes out and then goes down. And then over here, it goes down quite a bit through the x-axis, and it does that. And if you're in Math 31, you can see that I didn't do a fantastic job of drawing that because of the slant asymptote is not really consistent with the two curves. But that's not my point. Okay. Again, just to make sure, if you're not in Math 31, if you're not in calculus, don't worry about slant asymptotes. It's got nothing to do with anything. The important point about this graph is that there is a vertical asymptote at the non-permissible value for x, right? We said that x cannot equal to 2, and we get a vertical asymptote there. What about g of x? So can somebody just help me out? Was g of x x squared minus 3x minus 2, or plus 2? Okay. So g of x is x squared plus 3x plus 2. We'll clear out a bit of this extra garbage here. Oh, my mistake. Divided by, in brackets, x minus 2. So, and it's minus 3x. Is that better? Okay. X squared minus 3x plus 2. So this is a rational function. Well, what does it look like? Well, it looks as though it's a straight line. But it's not a straight line. That's not a straight line, because a line has no breaks in it. And yet we know there's a non-permissible value of 2. If I were to go to my table right now, I don't know what format my table is in. It's in the form where I can just enter in different numbers for, no, it's not. I've set it up to start at 5, or start at 0 and go up by 5. So I'm going to set up my table to start at 0 and go up by 1. And I look in my table. There's the graph again. I look in my table, and when x equals 2, there's an error. And what's interesting here, if you go back to your graph, and you go trace, say, -3, it'll show you the point where x is -3 and y is -4. If you go trace 0 it'll show you the point 0, comma, negative 1. If you go trace 2, there's no point. This is something that you want to try to wrap your head around, because if I go trace 1.9999, there's a point at x equals 1.9999. If I go trace 2.000001, there is a point there. We're talking about limits for you calculus people here. As x is getting closer and closer to 2, those y coordinates get closer and closer to some number, 1. That's of no significance right now. But the point is, you can get as close to 2 as you want, but you just can't reach 2. So there's a hole in the graph, but because you can get as close to 2 as you want, that hole is infinitely small. Now there's a way to see it on your graphing calculator. Depending on the function, if you're lucky and you go zoom decimal, which is zoom 4, most graphing calculators will end up showing you the hole. I mean, the size of that hole on the calculator screen is way too big, right? The hole is infinitely small, so you can't see it, but this is a way for you to visualize where it is. So what this looks like is a straight line. The precise details of this line, the fact that it has an x-intercept of, I believe, 1 and an y-intercept of negative 1 is unimportant. But that's not what the graph looks like. The graph looks like this. There we go. So it's not, this is, and I want to be very clear here, this is not a linear function. It's not a linear function, because a linear function wouldn't have any gaps in it. This is a point of discontinuity, or a hole. So we have a hole, or a point of discontinuity, at x equals 2. What's the y coordinate of that hole? Like, I want to see if you can wrap your head around this. When I go trace 2, there is no y coordinate on the graph, right? Because at 2, there's no point on the graph. But the hole itself has coordinates. The hole is located at x equals 2. What is the y coordinate? Miles? 1. Why do you know it's 1? Because it's approaching 1, right? When we went trace 1.99999, it's very close to 1. And you could kind of reason this out, that if you keep getting closer to 2 without reaching 2, the limit thing from calculus, that you're going to get closer and closer to 1. So this hole is actually at 2, comma 1. That is not a point on the graph. It's a point that's not on the graph. Right? The hole is not on the graph. Part of the graph that's not there. Okay. D, describe the difference between the two graphs in terms of the non-permissible value. Well, I've already done that. I think you've probably written it down as well, that there's a vertical asymptote at x equals 2 for f of x, and there's a hole at x equals 2 for g of x. That's the difference. Now, how would we know that without a graphing calculator? Well, there's a rule, and we're going to develop this rule right now. It says simplify each function and write a rule that connects the simplified forms of this to what we've discovered. Let's see. How do I simplify a rational expression? I factor and cancel. Right? It's the only way you can simplify a fraction is to cancel factors. Are there two numbers that multiply to give 15 and add to give negative 8? Well, of course, negative 5 and negative 3. So this factors into x minus 5, x minus 3. Well, that was a waste of time. Well, it wasn't really a waste of time. I've learned by factoring it that rational expression doesn't simplify. Okay? There's nothing I can do with it, but I wouldn't know that until I factor it. G of x, let's see, are there numbers that multiply are there numbers that multiply to give 2 and add to give negative 3? Yep. X minus 1 and x minus 2. So these cancel. G of x equals x minus 1. I have a question for you, and it's a tricky question, but it's an important question. Is it true to say that that's what g of x is?
No.
Why not? It's sort of simplified to give.
There's a hole that's missing. If you put 2 in for x, it would have given you 0 times over 0.
Right. So I'm allowed to put 2 into this highlighted function, which means if I graphed this function, and I'm going to do so right now. How do I want to do this? Let's go here, here. I'm going to capture this screen. There we go. Okay, so that's the actual function, and there's a hole there, right? In fact, I'm going to do that again. I'm going to do that again and show you the hole in the image I capture. So this is the function g of x. If I were to sketch now x minus 1, which is this highlighted thing that I've simplified to, this is not g of x, is it? Because this doesn't have the hole. So how do we write g of x then, if this is incorrect? And another way of describing what Miles is saying here is you're allowed to put 2 in for x here, but you're not allowed to put 2 in for x in g of x. Well, what we have to do then is say this. We have to say x is not equal to 2. And that removes that point from the function. And the rule is this. If the denominator that produces the non-permissible value does not cancel, you get a vertical asymptote. If the denominator factor that produces the non-permissible value does cancel, you get a hole. Okay? Does not cancel, you produce a vertical asymptote. Cancels, you produce a hole. Incidentally, even though x cannot equal 2 in g of x, what will you get if you put 2 in for x in the simplified form? 1, which is the y-coordinate of the hole, which kind of makes sense because you're not allowed to put x in, but if you do it anyway, you get the value that y is not allowed to be. And that's how we find the y-coordinate of the hole. So what are the domain and range of each function? I'm not worried about the range of f of x. That's just a big can of worms. It's messy. I don't want to deal with it. What is the domain? Each of these have a domain of x is not equal to 2. And the range of g of x is that y is not equal to 1, because 1 is the y-coordinate of the hole. And again, that can be found by putting the x-coordinate that you're not allowed to have on the function, in other words, the x-coordinate of the hole, into the simplified function. All right. Describe the behavior of the graph near the non-permissible value for each function. Well, as x approaches 2 on f of x, the function approaches positive or negative infinity. As you get closer and closer on the graph of f of x to x equals 2, the graph takes off to the sky and towards the floor. However, in g of x, as x approaches 2, f of x approaches 1. It's zero. Don't read too much in the word zeroing, but the y coordinate is zeroing in on 1. It's getting closer to 1. All right, any questions with that entire example? Biggest lesson to be learned, if the factor that produces the non-permissible value cancels, it's a hole. The y coordinate of the hole can be found by putting the non-permissible value into whatever's left. If the factor that produces the non-permissible value does not cancel, it's a vertical asymptote at the non-permissible value. Okay, determine the non-permissible value of x if any exists for each of the following functions. Well, this doesn't have any non-permissible values because, and I don't believe you necessarily need to write this down, but the idea is that you're thinking about solving this equation to figure out where the denominator is 0. Where does x plus 4 equal 0? Well, if I subtract 4 from both sides, I end up trying to solve this brain buster, which is impossible because you cannot take the square root of a negative. Over here, x is not equal to 2 or negative 2, and the reason is you're solving this equation. Well, you know, if you like, you're really solving, I suppose, these non-equations. It depends on how you look at it, right? I don't think we would ever be picky on an exam. You can put not equal to or equal to there. But when you get to what I've written in red, it's not equal to. This can factor into x plus 2, x minus 2. So the values of x that make the denominator 0, which is not allowed, are positive and negative 2. We've got a non-permissible value here of 4, and I hope that you would agree we don't need to write anything there. Just by inspection, 4 is the value that makes the denominator 0. And here we have a non-permissible value of negative 2. No problems? Okay. While we're here, let's factor the numerators, just because. This numerator factors into x times x plus 2. This factors into x times x plus 2. This factors into x times x plus 2. Are all of your numerators the same? Okay. This factors into x and x plus 2. So now in part B, I'm going to show you the equations again only because I need to look at them. You've already written down pretty much everything you need to write down about these functions. But for the functions with non-permissible values of x, which were the following. You don't need to rewrite this. You've already written it. I'm just putting it up here so that I can see it. Correct? Okay. Which of these correspond to holes and which correspond to vertical asymptotes? Well, we don't have any to deal with in f of x, but this is x times x plus 2 over x plus 2, x minus 2. And one of these factors cancels. The factor x plus 2 cancels, and the non-permissible value that came out of x plus 2 was negative 2. So the rule is that we are going to have a hole at negative 2. We'll get to the y coordinate in a bit. The x minus 2 does not cancel, and that means we have a vertical asymptote at x equals 2. Over here, this expression is x times x plus 2 over x minus 4. That denominator factor of x minus 4 that produced the non-permissible value of 4 does not cancel, which means we have a vertical asymptote at x equals 4. And I'm not going to spend class time today graphing these on the graphing calculator, but you can certainly play around with any of these and see what's going to happen. Over here, this is x times x plus 2 over x plus 2, while the factor that produces the only non-permissible value of negative 2 here in this last function cancels. And what that means is there is a hole at negative 2. Right? And we'll worry about the y coordinate. We could find the y coordinate now, but I think I'm asking you to find it in the next one. And I believe I've already kind of answered part of the rest of this question. Because this question, I just realized now, just simply said which are holes and which are asymptotes. C says write the equation of the vertical asymptote for the ones that have vertical asymptotes. We've already done that, right? C is answered there and there. What does D say? D asks us, I believe, if there's a point of discontinuity or a hole, what are the coordinates of the hole? Well, I've already got half of the coordinates of the hole, right? For g of x, the hole is at negative 2. How do I find the y coordinate of the hole at negative 2? And for you calculus people, you don't have to do limits. That's not, you could if you wanted to, but that's not where we're going with this. How do we find the y coordinate of the hole? How do we find this number? Yeah.
You put -2 into the reduced function.
Excellent. You put negative 2 into the reduced form for the equation of the function. And all I have left up here, let me highlight what I have left. All I have is x over x minus 2. So I put negative 2 in there, and I'm going to get negative 2 over negative 2 minus 2, which is going to be negative 2 over negative 4, which will give me 1/2. And the same thing goes over here. Well, I feel silly even highlighting this. The only thing that's left here in this final function in the reduced form is x. So when I put the x coordinate of the hole, being negative 2, in for x, I get, for this, negative 2. I apologize for my computer being so sluggish this morning. I don't know why it's moving that slow. Any questions with example 2? All right, let's take a look at example 3. Match the following graphs. Well, let's make some observations. We want to match some graphs with some functions. The observations I'm going to make are about the features of the graph that are non-permissible values. Here I have 2 vertical asymptotes. You can see they're at negative 2 and positive 2. Here I have a vertical asymptote. You can see it's at 2. And I have a hole. You can see it's at negative 2. Where we are going with this, everybody, is if there is a hole at negative 2, that means we need a factor in the denominator. We need a denominator factor of, I don't know that you need to write this down, but I'm going to, of x plus 2, right? Because the hole is at negative 2. If there's a vertical asymptote at positive 2, we need a denominator factor of x minus 2. In other words, we have non-permissible values of 2 and negative 2. What will be different is that because there's a factor that produces a whole of x plus 2, we need an x plus 2 in the top. Over here, by the way, you don't even have any non-permissible values for this one. So clearly, this is b of x. I shouldn't say clearly. I take that word back. When you look at these, there are no non-permissible values that can exist for that function because no value of x will make that 0. When you take a look at both of a of x and c of x, they both contain plus and minus 2 for non-permissible values. The difference is don't write things this way on an exam. That's pretty lazy work. The difference here with a of x is the x plus 2 cancels. Well, that's going to produce the whole. So this is going to be a of x, and this is 2x over x plus 2x minus 2. Well, none of them cancel, so this is c of x. Are we okay with example 3a? All right. B, I hope you're understanding that, well, a couple of things. You were not expected to know why these graphs looked like what they looked like. Okay, that's not what this lesson is about. You were expected to connect the non-permissible values in a graph to the factors that exist in the function. So the other thing you need to know then is, of course, that you have to factor everything first before you can draw any conclusions about what the graph looks like in terms of non-permissible values. L of x is x minus 1 over x plus 1, x minus 1. M of x is x minus 3 times x minus 2 over 3 minus x. Okay, let's start with k of x. Does k of x have non-permissible values? 2 of them, right? Is it 2 asymptotes? Is it 2 wholes? Is it one of each? What is it? Aiden, what do you think?
One of each.
One of each? It's only one of each if one of the factors cancels. This factor of x minus 2 doesn't cancel, so it's an asymptote. This factor doesn't cancel, so it's an asymptote. The key is whether the factors cancel or not. So this will have 2 asymptotes. This must be L of x, or sorry, k of x. What about L of x? Riley, will L of x have 2 asymptotes, 2 wholes, or one of each? One of each, good. And what will the x coordinate of the whole be? 1, excellent. Because these cancel, the whole is at 1. Oh, we got a whole at 1 right here. And a vertical asymptote at negative 1, this must be L of x. Which leaves this as m of x, but I want to explain why it's m of x. Do the 2 factors that I'm going to highlight, one in yellow and one in green, do these 2 factors cancel? It's a bit of a loaded question. Miles? Meaning it's
Cancel if you take negative 1.
okay, so they do, not right now, and I know that some of you would have said, yeah, they cancel, and we're going to put a negative 1 somewhere. But they don't cancel right now. However, if I factor a negative 1 out of It doesn't matter, but I suspect most people would factor the negative 1 out of the bottom. The 3 becomes negative 3, the x becomes positive x. Now they cancel. So what we're left with is negative x minus 2. Of course, x is not allowed to be 3. And that's why that one has a hole, and that's why it's m of x. By the way, if I put 3 in here, 3 minus 2 is 1. Negative 1 is the y-coordinate, and you can see the y-coordinate is negative 1. Any questions at all with example 3b? Right. Finally, now example 4, I find that there's one other thing I have to teach you, and it just comes across better in an example rather than part of a lesson. What's the equation of this rational function? This, everybody, has nothing to do with h and k. Nothing. Okay? What you're going to say is that the function must contain an x minus 3 in the denominator and an x plus 2 in the denominator. Why? Yeah.
Because of the hole in the vertical asymptote?
Right, because of the hole at x equals 3 and the vertical asymptote at x equals negative 2. In other words, because there are two non-permissible values, right? Negative 2 and positive 3. So those are the zeros of these two factors. This also needs to contain a factor of x minus 3 in the numerator. And the reasoning here is the x minus 3 has a 0 of 3, and the hole is at 3. Again, you're focusing on this rule that wherever there's a hole, that factor that produces it has to be on the top and the bottom. Okay, it has to cancel. However, if you graph this, let's take a minute and let's graph this. And we have to be very cautious in entering this. It's x minus 3 in brackets divided by, if I were to enter this, my graphing calculator is going to think I want to divide by x minus 3 and then multiply by x plus 2. So I have two options. I can either put another set of brackets around those two binomials in the denominator, or you could just do this. You could just take a moment of clarity and thought and multiply out x minus 3 times x plus 2 to get x squared minus x minus 6. So I'm going to set up my window settings to match this. My window settings should then go from negative 11 up to 7, and vertically from negative 10 up to, and vertically from negative 10 up to 10. And this, I didn't do that right, obviously. What did I do? Oh, negative 10 up to 7 and negative 10 to 10. This graph looks nothing like this. I mean, there's a vertical asymptote at 2, but first of all, there's a horizontal asymptote here. I don't know if you can tell. Do you see there's an x-intercept of negative 4? If I were to go trace negative 4, that's not on the x-axis. This is wrong. If I were to go trace 3, am I going to get a hole? Well, yeah, I'm going to get a hole because I've entered x minus 3 over x minus 3. What's the issue here? The issue is the x-intercept. Now think about this for a second. If this is at negative 4 comma 0, that means when you take negative 4 and feed it in here, you have to get 0 for y. Y is f of x. what's the only way this can be 0 at x equals -4? I'll start with a simpler question. What's the only way a fraction can ever equal 0? Yeah. If the top of it is 0. Well, how can the top of this be 0 at -4? If we put an x plus 4 on the top. And if I do that now, if I go back to my graphing calculator, and I insert an x plus 4, and I really hope that you're aware, it doesn't matter the order in which I write the x plus 3 and the x plus 4. And I graph it now, I'm even going to go zoom decimal in the hopes that we can see that hole. Yep, there's the hole. And you can see that the x-intercept is -4. You can kind of see that there's a vertical asymptote at -2. And the thing that's going to puzzle some of you is some of you will look at these questions and go, well, how do I take into account the horizontal asymptote? And the answer is you don't. It happens. Okay? If you build your function by putting factors that are non-permissible in the denominator and identical factors in the numerator if there's a hole, and factors for an x-intercept in the numerator, the x-intercept, or the horizontal asymptote, finds itself. Factors in the denominator of a rational expression produce non-permissible values of x. If the factor can be canceled with an identical factor in the numerator, then there's a hole at that point, and the y-coordinate can be found by subbing in the x-coordinate of the hole into whatever's left. And if it does not cancel, then there's a vertical asymptote at that point. And the last thing is the extra layer of information I added in the last example. If you have an x-intercept, you need that factor in the numerator. Now there's one other issue, and I don't know the likelihood of you encountering this. But when I say entirely, I mean this. If I gave you a function we would have, by the way, an x-intercept at -1 because there's a factor in the numerator. When I say there's a factor in the numerator, I mean it doesn't cancel. Okay? It means after everything is done, you still have it there. There will be, so I'm going to write this down, an x-intercept at x equals -1. We will have, I hope everybody is clear that this is going to be the case. Now, will you have an x-intercept at 2 because there's an x minus 2 in the numerator? No, because it's going to cancel. Will you have a hole at x equals 2? No, you won't. Because when you cancel that x minus 2 on the top with one of these x minus 2's on the bottom, you're still left with an x minus 2 on the bottom. That's what I mean by entirely. Okay. On the other hand, there would be a hole at 2 here because those denominator factors go away. You wouldn't get an x-intercept there because there's a non-permissible value. It would be a hole. So I don't know the likelihood of you seeing that kind of thing, but that's the gist of it. You can see the assigned problems.